Thank you, Raghav, and thank you, Praveen. Thanks to the START team for this nice initiative once again. Within the limited time, I will try to cover the future directions and challenges in astrochemistry. If you look at the slide here and the title, Simulating Space in Laboratory, it is one of the big challenges in astrochemistry. And when you say simulating space, the question arises. Hope you'll be able to see my cursor. Yeah, the question arises whether you simulate the low temperature part of the space or the high temperature part of the space. We're going to look at it now. Right. Whether you call space is void of nothing, I mean, void of things, but there are observations that they say that, space is full of molecules, or at least some elements are always present. So, keeping this in mind, people were looking for many molecules from simple to large molecules, not just in the deep space, which you see in the background here, but also on the solar system objects. And while we say that simulating them in the laboratory, we have to bring all these conditions where molecules exist and atoms do exist in the laboratory that you have on planet Earth. Okay, right. So you can say laboratory astrochemistry. So it's a big challenge. But before we go to that, just want to show you this photograph. When we showed this to students, I'm sure that many students are attending this lecture, and we showed this to students, the initial thought comes to their mind, oh, this is something to do with the stars. There's plenty of stars, and maybe some of the answers were like some supernova were exploding on that. But no, it's not a star or a supernova. What you see now, you see there's some sort of eye at the center. It is not a star, rather it is the image from Chandrayaan 2. And what you see the eye, it's a crater. Okay, so all that you see is not always deep space. Next, there is one of the lines that is given, that astrophysics and astrochemistry. Well, the importance of astrophysics, which you used to say, comes from helium, because the element helium, which is in demand globally for research and of course for celebrations, which is usually filled in the balloons. It was discovered in the year 1868, but not on planet Earth. It was discovered not on planet Earth. It was discovered in the sun. Okay, and then it was found to be present on our planet Earth. Right. So you see that we have to understand the neighbors, not just looking at what is happening on planet Earth, not just the chemistry on planet Earth. You need to know what is happening around Earth. When you say around Earth, not just the near Earth asteroids, it has to be the inner solar system as well as the outer solar system. Okay, so when we talked about helium, let us also see what is the connection between these elements and the planetary science. Because astrochemistry has its legs almost in every part of the science, that starts from astrophysics to astrobiology to planetary science, and even in material science, in geology, and so on. So when we talk about the element, let us briefly see what is the connection to the planetary science. How they named the element uranium. They named it after the planet Uranus. So the discovery of another new element after uranium, how do you think they have named it? Certainly, yes. Some of you, many of you would have got the answer. It was named after the planet Neptune, so it is named as Neptunium. Then the discovery of another new element after Neptunium came, and how they would have named it. By then we know that Pluto exists, so they named it after Pluto. So it's Uranus, Neptunium, and Plutonium are aligned in the same way, like those planets which are aligned in our solar system. So now you go back to your periodic table, and you will find these planets aligned so well. It's just honoring the discovery of planets, right? So there is a good amount of interlink between people who does atomic physics and molecular physics as well as the planetary science, right? But what about the molecules, the biography of molecules? Why we call the biography of molecules? The moment atoms exist, they tend to form molecules. Chemistry has to be there. We do not know what sort of energy is involved in making a molecule, but definitely there is some chemistry. But the question is, what is astrochemistry? Uh, you must have heard of physical chemistry, inorganic chemistry, and organic chemistry, but what is astrochemistry? When the question comes, more than astrophysics and astrochemistry, let us discuss this part of it. What is astrochemistry and what is called cosmochemistry? I used to ask this to our students. Many places, students have come up with answers saying that well, cosmochemistry is the study of reactions in some part of the extreme conditions in the solar system or beyond, whereas astrochemistry is some other different phenomenon. Lot of answers tend to come, but we tend to ask them, then what's the difference between astronaut and a cosmonaut? Okay, but anyway, we'll directly go to the answer. Astrochemistry is the study of molecules, and whereas cosmochemistry is mostly the study of elements. Okay. Now, so in that case, if you say astrochemistry is the study of molecules, we can briefly say that it is the fate of molecules beyond Earth. When we say beyond Earth, away from Earth, up to deep in space. Okay, right. So one of our members in our group, he put it like that, saying that it's a biography of molecules beyond Earth. Definitely, yes, it's a biography of molecules beyond Earth. But where does it link to us? According to Carl Sagan, it should be called as autobiography of molecules beyond Earth, because he says, of course, we know from the scientific proofs now that we are all stardust. So it's an autobiography of molecules beyond Earth. Certainly, yes. So what about the space between the stars when you look at the night sky to date? Even now, there will be empty space when you look at the night sky, apart from the places where it's bright light, the stars. It is the interstellar medium, the space between the stars, and this is the place where new stars are being born. Okay, perfect. So now we know that chemistry is happening even far from Earth, much much away from the solar system. So what we know about those chemical reactions which are happening there? Let us begin from the chemistry on planet Earth, where we begin. Okay, where we are right now. Right. So what about the electromagnetic spectrum? It helps us to understand what chemistry is going on. Okay. But without electromagnetic spectrum, uh, yes, scientists were looking at chemical changes for quite some time until we understood the use of electromagnetic spectrum, the spectroscopy part. But before that, yes, lots of fossil fuels being burnt, and we have this internal combustion engines burning lots of fossil fuels. So it's artificial chemical reactions are happening. But when you say the internal combustion engine burning the fossil fuels and so on, after the advent of spectroscopic techniques, when they looked at the residue that is coming out of, which is called the soot coming out of the auto exhaust, they looked at the spectrum of the auto exhaust, and then they looked at the spectrum of deep space. There is a similarity between them. Okay, so there is something being made, and artificially what we make, both of them have some similarity. So there's a strong chance that the chemistry is more or less similar, whether it's happening in the internal combustion engine or deep in space. Right. As if you talk about chemistry on planet Earth, another way which you have mostly come across, the lighting of camphor. Okay. So when you light camphor, within a few centimeters, you see this black residue coming out of it, within just a few centimeters. Okay. Please go back to your home after all the lectures today, and then try to see it. If you have not noticed this before, definitely would have noticed. You may see that the carbon residue starts coming, and then if you Google about the residue from camphor, you may see that lots of aggregates are being shown using the field emission scanning electron microscope. Right. So these residues contain the oxides of carbon and nitrogen, and a lot of particulate matters. In fact, there's a lot of hydrocarbons embedded within it. What you see burning there and what you see burning deep in space more or less have some similarities. Similar processes might be happening in the deep space, which you have seen in this slide, with the spectroscopy telling us that we are looking at something same. Fine. But that is to do with heat. But what about low temperature? Because the moment you go out of the sunlight, you are feeling very cold. So the cold temperatures are more common in the solar system wherever the sunlight doesn't fall. And if you go away from the sun further away, definitely it is getting cold. So we're going to talk about something called the ice. It's not an ice cream or the water ice, what we handle at home. If you talk about ice in an astrochemistry lecture or in an astrochemistry discussion, it is any molecule that is frozen. So it is not just water, it is not just the CO2 which is called dry ice, it is any molecule that is frozen. That is going to be the meaning for the words that we are going to use in this entire lecture. Right, so we saw the chemistry on Earth's surface. Now we are going to the Earth's atmosphere. As atmosphere chemistry, yes, the most famous molecule, ozone, which comes from the oxygen atom. They combine to make oxygen molecule. Of course, they again dissociate, where you need another oxygen atom to make an ozone molecule. This is very, very famous. The Hartley band, which is saving us from the harmful UV radiation that does not, if it does not exist, then most of our DNA will be absorbing this radiation and the DNA strands will break. We'll have issues. So that's why we say ozone is protecting us. So is that the only thing which is happening on our on our Earth's sphere? Certainly not. There are lots of reactions because energetic particles that are coming from the sun, let it be the X-ray, the vacuum ultraviolet, and so on, they are being absorbed by the atmosphere that we have got. Okay, right. When you say vacuum ultraviolet, I'm sure for many of you this is a new word, this is a new term. The vacuum linked to the ultraviolet. Okay, UV spectroscopy of the ultraviolet, which is known to you, has a wavelength range which stops at 220 nanometers. If you go below that 220 nanometer, you're entering the region called vacuum ultraviolet. This region, vacuum ultraviolet, is having the photons have higher energy than the ultraviolet photons. Okay, so these are being stopped at the Earth's atmosphere. So the moment energy is deposited on the atmosphere, you are looking at chemistry. Chemistry can be driven. So how the chemistry is driven now in this case, that these photons can generate secondary electrons. Okay, so that becomes a new player as you move away from the Earth's atmosphere, surface towards atmosphere and above. You're looking at a new player, which is the secondary electrons. So now you are moving away from the atmosphere, so eventually you're moving much more away, and then you reach the closest neighbor, our moon. The moment you reach our moon, we don't have an atmosphere there. So what we call there, it's called an exosphere, okay, which does not contain dense atmosphere. So what is the difference between atmosphere and exosphere? An atmosphere is where the molecules are plenty and the distance between the two molecules are of the order of few microns. Whereas in an exosphere, the two molecules don't collide that easily. They're far away from each other, of the order of few kilometers. Okay, so the moment you go to the Earth's, the moon's surface, you're getting more players, which is now from the sun, the photons or the ions. Okay, the particles like such as H plus, which you call as protons, or so on. Right now, the chemistry is totally driven by the energetic particles that are coming from the sun. Okay, so now you are entering a place where there is not enough atmosphere to protect you from the harmful radiation. So the energy is being dumped from as possible, as much as possible, from variety of sources, from the sun, from the cosmic rays. And now when you move away from the inner solar system, you'll get a lot of particles from the Jupiter's magnetosphere. And if you move to the Saturn, you will get those particles from the Saturn's magnetosphere will be influencing the chemistry. Right. But instead of moving much away from the inner solar system, is there a place in the inner solar system where you can look at the conditions that you get on the Jupiter's moons or on the Saturn's moon? Certainly, yes. If you look at the permanently shadowed crater on our own moon, where you can see the temperatures are very, very low. So you are looking at an analog condition of on Jupiter's icy moon or a Saturn's icy moon. The temperatures are very, very low here. It is not just one crater where the temperatures are low. If you go to the south pole of our moon, there's plenty of places which has not seen the sunlight for ages, for millions of years. So this is one of the reasons that many of the space agencies are interested in the south pole, where it is still primitive. Lots of new things can be learned, and there is one big challenge for the Chandrayaan sample return mission, which I'm going to touch in the last slide. Okay, right. So the chemistry on our moon, if you take water and carbon dioxide, which is the plenty over there, which is seen in this image, the product that you can get from water and CO2, carbonic acid. That's what you drink in your soda. So you can say the molecules that you drink in your soda are also present in the other places of the solar system. But yet there is another challenge. There is no definitive confirmation of this molecule known to date in the solar system. This is something very interesting. See, we know that the simple molecules are present and the product of these molecules are quite possible, but it is a challenging it is a task even today to confirm that this molecule is present. Okay, right. So now we move from the moon to some places where it has some atmosphere, a little bit of atmosphere, not like Earth. For that, Mars is a good candidate. Mars has a lot of carbon dioxide. The moment carbon dioxide is there, it has plenty of oxygen in relative terms, because there's two oxygen with the carbon. Then there's a series of reactions which end up making ozone. So Mars is the first place after Earth where ozone has been discovered. Okay, right. But is ozone helping uh, the surface of Mars by covering the vacuum ultraviolet photons not reaching the surface of Mars? Certainly not, because the density is very less. So it won't be able to protect all the surface of Mars at one time. I mean, in the day inside of Mars at one time, to remove the harmful or to absorb the harmful vacuum ultraviolet radiation. Okay, so that's why you need a very good density. The atmosphere concentration has to be very good if you have to protect yourself from the chemistry that is happening because of energy that is coming from the sun. Right. So now, instead of going away from the solar system, let's move inside the solar system. If you go to the first planet, Mercury. Mercury is not a place where it is only hot, but there are places on the north pole of Mercury where the sunlight does not reach. Okay, so it doesn't matter how close you are to the sun, as long as the sunlight does not reach, the places are going to be cold. So you can still have your ice cream sitting on the north pole of planet Mercury, and you can enjoy your ice cream because there are colder places. Even the molecules stick there to make icy layers. Okay, right. Now if you look into the entire solar system, the outer solar system part, it's far away from the sun, so definitely the temperatures are very so. A small comparison of a few moons of Jupiter, Saturn, and Neptune and Pluto, plenty of molecules are available, and depending on their sublimation rate, at what temperature they sublime, you can find variety of molecules being present in the frozen form, which is the ice phase. Okay, but so in this case, is there any new player to start the chemistry because it's far away from the sun? Sun will be definitely influencing. Is there any other candidate? Certainly yes. I have told you the magnetosphere. You see the different moons here of Jupiter and Saturn. Okay, and what I have shown here, it may appear like you are looking at moons of Jupiter, Saturn, or Neptune or something. No, these are the underside of the frying pans, which I got from one of the posts from Facebook long back, several years back. Some anonymous person added. So it is not the moons; it is the underside of the frying pan. So the different colors that you see here tells that what sort of chemicals or the masalas that one has used for their cooking. So now the same thing happens for the moons. The moons have different composition. Io, for example, the first moon of Jupiter, Io has a lot of sulfur. Okay, and the other moons don't have that much of sulfur, so the difference that the way you see Io will be totally different, which will be more yellowish than the other moons. So there's some sort of a painter which is in working uh, mode, and that painter in the scale of a solar system object can definitely be a larger component of it is the magnetosphere. So this painter, the magnetosphere, they pick the ions from one object of the Jupiter's moon, one moon of Jupiter, and they take it to the other moons. Okay, and how happens? If suppose for Io, which has these cryovolcanic zones, when they eject the molecules out, Of course, the cryovolcanism, the particles come out as ice. It's not like a hot volcano that you see on Earth. And the molecules come out, they get ionized by the sun's photon. The moment it is ionized, Jupiter's magnetosphere takes away these particles, these ionized molecules, and then it then accelerates towards the other moons. Okay, and that's how the other moon starts getting more sulfur. Of course, there are other ions that can go, which is known from the Voyager flyby, but sulfur is a lot because of Io's presence. So this is a simple diagram that shows you that the magnetosphere has this the magnetosphere has this influence on the satellites which are well within the magnetosphere. Okay, and then they get these ions going around. So this is one of the new players that is initiating chemistry. It's not just initiating chemistry. In the case of sulfur ions, they also engage in the chemical reactions. That's how it will be happening, which you can see. When an ion gets implanted, you get a lot of secondary electrons being generated, and the ion get neutralized, and the atom finally end up in making a new molecule. It's not just with Jupiter, with Saturn also we have the same thing. Just a pictorial here. Saturn is there, and you see the moons, Saturn, Enceladus, Tethys, Dione, Rhea, and this is Titan. Titan has lots of nitrogen, plenty of nitrogen, right? So the nitrogen ions are more close to Titan, and this has been towards other moons you have a lot of protons and oxygen plus. So there's sort of chemical exchange happening between these moons, and magnetosphere is responsible for all of these. So if any of you have not seen the real Saturn system, this is one of the photographs from the Cassini. What you're seeing is not a Photoshop. It is a real photograph from the Cassini spacecraft. Okay, you see 5 moons there. This is Rhea. These are the other moons. This is a quintet of moons, 5 moons along with the disk. Right. So as I said, there is a possible chemical transfer between the moons, and which is known to be responsible for from unknown species on other moons. Okay, so the chemical transfer is also proven to be happening between the moons. Right. Not just that. Recently, the one which we talked about, the ozone on Earth and so on. Recently, we had the evidence for the presence of ozone on one of the moons of Jupiter. One of the moons of Jupiter, the moon Callisto. Okay, and what the spectrum, what you see is from Hubble Space Telescope, and this band here, what you see is the famous Hartley band, where ozone's presence can be confirmed. Okay, so ozone is not just on Earth or Mars; it is there also on the Jupiter's moon, which is known from the year 1996, 1997. But still, there is plenty of room available for our young generations to discover new things. Okay, so you see this one came in the year 2020 and around the end of 2023. So there's some of the future things that can be considered. It's not like everything has been explored in the solar system. Plenty of things still unknown, right? And one of the places what you can look for is the lunar south pole. Okay, right. When you say the lunar south pole, on one of the places, you see lots of damages have happened here. These are called the craters. And now these craters they come from it. Okay, the craters on the surfaces. So the impacts are inevitable. The physical and chemical changes are happening because of these impacts. Not just our own moon, anywhere in the solar system you see, there's a lot of impacts that are there, even up to the Pluto system. On only one portion here you see where the impacts are kind of erased because of some of the geological activities. Otherwise, there's plenty of impacts in every object in the solar system. And that impact brings physical and chemical changes. Fine. So, what chemistry can be happening there, and what we know about that so far? So far in the school, we know that the Arrhenius equation almost controls everything about the chemical reactions. It constant as a function of temperature. Okay, but I leave it to you here. If you go very much low in temperature, okay, up to 10 Kelvin or so, whether you can use this equation or not, I leave it to the students to work on this. Right. Now, if you go beyond Pluto, it's neither it is not even far from impacts. We have plenty of impacts happening on these objects, and in our generation, we are very lucky. We know how the objects beyond Pluto look. So chemistry is happening everywhere in the solar system, and impact is also happening everywhere in the solar system. The more you go away from the solar system, the influence of radiation keeps reducing. Okay, that's one thing, but the impacts keep happening everywhere. It doesn't matter wherever the object is. So the chemistry is there everywhere here, right? But is there a way that we can simplify this? Certainly, yes. And is there a place that you have come across astrochemistry in the past? It's not just during this lecture or anything that you've seen online. You have studied astrochemistry in your school books when you came up across this equation PV equals nRT. This is the place where if you replace the temperatures of deep space, you can get the conditions, the pressure and other the density conditions deep in space. Okay, so deep in space, I think I'll be finishing in another 5 minutes or so. So the chemistry beyond away from Earth can happen in solid, liquid, and gas phases. But mostly we are at the moment looking at in solid and gas phase, because beyond Earth, wherever you have the liquid being present on a solar system object, isn't that much so far. Okay, but what we know, right? So when you say it's more of solid happening in a very large object and so on, certainly not only in the large places. The chemistry is even happening in the nano factories, such as this interstellar dust. Okay, this dust is of the order of a few micrometers that you can see, and this dust, when the moment when it is very cold, it starts gathering all the molecules whichever is hitting this dust. So the molecules get stuck to that dust. They make an icy layer, and then it is now having a lot of molecules, which is like the reactants are ready, and the chemistry has to be initiated, right? So how the chemistry can happen if it is not a molecule, rather it is not just a molecule, rather it's an atom. Then these are the processes that can initiate the chemistry. You see, two atoms can accrete, and they can diffuse, they react, and then they can go off the surface. Whatever it is, the dust is very, very important. And the other future directions in astrochemistry, the most important thing in the difficult thing in simulating astrochemistry in the laboratory is that the astronomers keep on finding new molecules in deep space, and they keep, announcing that, oh, many new we have found benzene. Even now, in the year 2020, in the year 2010, they have found fullerene C60. So it's a large molecule. But even now, this year, the 2024, just a month ago, they have reported pyrene molecule, which is close to making the molecules of life, such as the nucleic acids and amino acids and so on. Pyrene has been discovered, cyanopyrenes have been discovered. So we are in need of many laboratories, many researchers who can take up this area of research and try to solve the problem, like how these molecules could have come in space. They said in 2010 they found the big molecules, C60s and C70s, but in the year 2021, astronomers have reported nearly 41 molecules to be present. This is quite a lot. That is deep in space, but what happens when you look into the number of molecules on a cometary surface? It's much more, because the spacecrafts have been going to the cometary nucleus and they find lots of molecules. But the problem here in astrochemistry, when you compare it with your textbooks, what is a simple or a complex molecule? A simple molecule or complex molecule depends on how we look into it, because on planet Earth you can answer, okay, it's a simple molecule which is smaller, and complex molecule which is larger. But in astrochemistry, it's quite hard to say, because a molecule which looks simple with four atoms, but all four atoms are different, have been discovered. It's very difficult to say whether this is simple or complex. Okay, because the formation pathways can be different. So we have been seeing a lot of this low temperature part, which is a 10K, but there can be even high temperature part. So there's plenty of things we are going to look at in astrochemistry. So the moment you go from ice to the high temperature and so on, that is where we have the difficulty. And we have come across calling the chemistry that is happening within the solar system or in deep space, which involves the dust, of course, the gas and so on. We start calling them as astromaterials. Okay, and this is my last slide, where you can see that Yeah, you can see, not the last slide, I have 2 more slides where you can see that there is an interlink between, of course, everything that you have been looking at on the surface of the moon, or the surface of our own moon, or the surface of moons of Jupiter, Saturn, or the macaron dust that is in the interstellar medium. But eventually, everything is towards making the molecules of life, or even the final thing, which can even be the first cell. That's where astrobiology comes into picture. So whatever the molecules that are being made from this tiniest of grains, which is in the deep space, or the surface of objects in the solar system, whether it be the high temperature or the low temperature, they finally tend to make some molecules that are very close to you, the amino acids, nucleobases, and the sugars. Of course, everyone is trying to address the problem on the origin of life, and the I've given meteorites here, and the evidence that we have got from meteorites so far. Meteorites are known to contain plenty of molecules of life. In fact, depending on what variety of meteorite it is, they will be telling us that, you know, we have to understand the processes that has happened in the solar system, in the many stages of its formation, and even now what's happening, and we will be able to crack that how it has originated finally. But when we say that, it looks like such a big dream, or it is a very extensive work. Definitely, yes, it is an extensive work. So it's not like one lab or one person can do this. You have to work with many labs where you can try to address these problems. So there are few labs that are working on this in India, and abroad, of course, we depend on a few of the facilities for the VUV, for the vacuum ultraviolet photons. In India, we have the RRCAT, where the Indus 2 VUV facilities are being are almost ready now for research. So this slide will give you an idea of the facilities that has been used so far to address this, to address a few problems. Of course, there are plenty of them which you are yet to address. Before I conclude, some students may be willing to know that how we say that there is some molecule on moons of Jupiter, some molecules on our own moon, and so on. So to help them and let them play with these spectroscopy components, if you go to PRL and look for this astrochemical ISIS database, on the top you see vacuum ultraviolet data. Search for it and search for aerospectral data. You don't need to log in. Login is only for the data provider, not for you, not for those who want to look at the data. These are the data which is in infrared and the vacuum ultraviolet, which you can download and you can play with. Okay, and you can see that how these spectrum are being used to match with the space-based data, such as the Hubble Space Telescope, or the telescope which had data in the infrared, the Spitzer Space Telescopes, and so on. And you can get a feel of how the problems are being solved. And this is my last slide, but before I conclude, the major challenge that we have right now in hand with the Chandrayaan sample return mission is that to date on the lunar samples, organics have not been found. They are very much limited. So if we find organics from the lunar sample, that'll be fantastic, especially if we find molecules such as the molecules of life, amino acids or nucleobases from the moon, from the lunar sample return. That'll be more brilliant. And to date, this is what the laboratory astrochemistry has got from simulating the conditions of the moon, that these molecules must be present because we have all the ingredients which is needed for making these molecules. And On top of this, we also say that our moon has to have certain amount of graphene because of the carbonaceous meteorite that are impacting on the moon, which eventually produces plenty of graphene. So sample return mission has all the capability to find whatever we see on planet Earth by simulating space. So there's plenty of room to investigate more. I stop here. Thank you.